Hello, my name is Tyler Ehrlich, and I'm part of Group 3. I'll be talking about the interatomic distance. Interatomic distance is the distance between the centers of two neighboring atoms. It is an essential property because it tells us how tightly atoms are packed and how strong their bonds are. The two metals that we are studying are iron and aluminum. We're starting with iron. Iron actually changes structure depending on the temperature. At room temperature, it is in a structure called body-centered cubic. As you heat it and it reaches 912 degrees Celsius, it changes into a face-centered cubic structure. If you keep heating it to 1394 degrees, it returns back to a cubic body structure. The actual value of the interatomic distance is 0.284 nanometers. This is the graph of the attractive and repulsive forces combined. As you can see at the lowest point, as you can see at the lowest value of E, which is the energy between bonds, that is where you will find the value of R, which is the interatomic distance between the center of each atom. The distance between the lowest point of E and the line E equals 0 is the potential energy of the bond. Aluminum, on the other hand, has a structure called face-centered cubic structure. This again is the graph of the attractive and repulsive forces combined before aluminum, which again shows the lowest value of E, which is the energy between bonds, and that is where you will find the value of R, which is the interatomic distance between the center of each atom. Also, the actual interatomic distance is 0.404 nanometers. The slightly larger distance and lower density give it properties such as being lightweight and an excellent conductor of electricity. The less densely packed aluminum makes it more malleable. Iron is extremely versatile, which is why it forms the basis of steel, which can be forged to be stronger or more flexible if needed. This is what the interatomic distances are and how they affect the material. Next, Andrew will talk about Young's modulus and bulk modulus.
My name is Andrew Horn, and I am also a member of Group 3, and I will be discussing question 2, which is about the elastic modulus and the bulk modulus of iron and aluminum. The elastic modulus is a measure of a material's resistance to being elastically deformed. For iron, it is 240.2 gigapascals, and for aluminum, it is 63.36 gigapascals. The difference between the two values for aluminum and iron shows that iron resists elastic deformation significantly more than aluminum does. The bulk modulus of a material is a measure of how resistant that material is to compression. More specifically, it is the ratio of the increase in pressure imparted to a material and the subsequent reduction in volume of that material. For iron, the bulk modulus is 190.6 gigapascals, whereas the bulk modulus of aluminum is 68.18 gigapascals. Much like the difference between the elastic moduli shows that iron has a high resistance to elastic deformation, the difference between the bulk modulus of iron and the bulk modulus of aluminum shows that iron also has a smaller decrease in volume when compared to aluminum at the same pressure. What this means is that iron has a higher resistance to pressure than aluminum does. And this is the formula for elastic modulus. It is negative 1 over R times the second derivative of the total energy. Now I will pass on the camera to the next person in the project.
My name is Liam Mosier. I am from Group 3. I will be discussing part 3 of our project, which is about vacancy and vacancy occurrence probability. To start with, we'll be talking about iron. We found our iron vacancy formation energy to be 1.4 electron volts. To find our vacancy occurrence probability, we took N over Na is equal to E to the power of our vacancy energy formation, to the negative vacancy formation energy, over the Boltzmann constant times the temperature in Kelvin. T here is assumed to be 293 degrees Kelvin, which is room temperature, or about 20 degrees Celsius. For N over Na, we found that to be 8.72 times 10 to the negative 23%. Therefore, 8.72 times 10 to the negative 23% of all sites within the 1 cubic meter of material will be vacant and not have an atom within it. For our actual number of vacancies in a 1 cubic meter of material, we found there would be 7.4 times 10 to the 4 vacancies. Next, we have our aluminum sample. For our aluminum, we found our vacancy formation energy to be 0.69 electron volts. Again, we use the same formula we used before to find our concentration percent probability of vacancies. N over Na equals E to the negative of the formation energy over Boltzmann constant times temperature. Again, we assume temperature to be 293 degrees Kelvin, which is the same as 20 degrees Celsius. This was equal to 1.38 times 10 to the negative 10% of sites, meaning 1.38 times 10 to the negative 10% of sites will be vacant. That means, for our N, we found that 8.36 times 10 to the 18 sites overall were vacant and would not have an atom within its site.